Greetings of the day. I'm Venkatesh, and I'm working on the topic of humanoid robotics at IIT Kanpur under supervision of Professor Ashish Datta. This is my third PMRF review. So I have been working towards the goal of push recovery control uh, of a biped with its legs on offset horizontal surfaces. I am also developing a hardware in loop simulator. I have been using Mujoko for all my dynamics and control computations. Here is a simulation of biped balancing on one leg. Uh, the inputs, the actuators is uh, its torque, which is not practically possible. However, we can do this in simulation. We have also implemented LQR control. I have also simulated LQR control here. Let us move towards more important things. So inverse kinematics is an important building block of any of the higher goals of trajectory planning and push recovery. So we are talking about a 12 degree of freedom biped, and it is intuitive to supply the information of the position and the orientation of the hip, right foot and left foot. Since this is a 12 degree of freedom, we do not have any redundancy or the number of equation of motion and the number of equations and the number of unknowns, that is the number of joint angles, are equal in this case. The reason we have chosen numerical method is we want to support a non-intersecting or skew consecutive joint axis at hip and ankle, as you can see in this top right figure. The module works faster than real time, around 10 iterations, more than 10 iterations finished within a millisecond or so. We are planning to publish this as an free utility. These two are examples of using trajectory tracking for real-time control of biped robot. So we have torso, which is moving horizontally. So this frame has been commanded to move horizontally. And here we also have prescription on the angular motion of the torso. Both of these trajectories are tracked with satisfactory error performance. Next, we move to the topic of push recovery. Instead of controlling the torso position, we control the center of mass position here. Now, ankle strategy is mainly about applying opposite torques to the disturbance. So it happens when we try to control the center of mass position in the prescribed position in the support polygon. We also control the torso orientation and maintain it during the course of motion. This module is called center of mass based inverse kinematics. This kind of approach has been used in literature. So it can accept the positions and angular positions, and it can also accept velocity inputs of the center of mass and the torso omega. In ankle strategy, this is just a set point control, so these inputs are 0. However, in the hip strategy, once we sense that the ankle strategy is reaching its limits and the fall is imminent, we prescribe angular motion to the torso. Now, how is this angular motion prescribed? So this is a two-phase strategy, again inspired from the literature. So in the first part, the torso pitches about the probable tipping axis. So this tipping axis K is identified, and the torso tipping motion or the torso pitching motion about that axis is defined in two phases. So we'll see it how. So the motion can be derived from a simplified model or faster than real-time full body simulations. So this strategy essentially works on the principle of reaction wheel. Reaction wheel can move, only it has limits up to which it can spin. So this is ankle strategy, not able to withstand the push. And here we have hip strategy, which can withstand the same amount of push. So you can see the motion happens in two phases. First, we absorb the push, by applying torque in the same direction, and then we recover. So this happens not only in sagittal plane, but also in any direction. So you can see here, the force is being applied in uh, to an angle with respect to the sagittal plane, and the tipping axis is somewhat uh, like around this green line here, and the tipping angle is prescribed by faster than real-time simulation. But this simulation is only for the phase one. It does not include the recovery part. So you can see the robot, it's falling back. Uh, Here are two practical experiments, physical experiments. If the robot is kept rigid, then it falls. If uh, we apply the principle of reaction wheel, then the robot comes back. To make this experiment more robust, and so we have now added capability of applying force in any direction because of this ring that has been put around, and a crisp pendulum and a crisp impulse can be given with this pendulum kind of setup. And FSRs are used to measure the impact force. Calibrated FSRs are used to measure the impact force. Moving on, uh, so a lot of work has been done for push recovery of a robot standing on planar ground. So we moved to stepped terrain. The concept of COP ZMP is still valid here because the ground normal is invariant. So the expressions for ZMP can be used as they are. Instead, we just have to use the whole ZMP axis, a suitable point on that. So the generalized COP ZMP is defined as a point on the which is on the line segment joining the foot uh, center of foot COPs based on the amount of reactions, uh, based on the amount of loads that the feet have. So this generalized ZMP is of limited use until we have the corresponding support polygon or corresponding bounded region to define stability margin. Uh, we can see that this generalized ZMP lies in the prismatoid defined by the foot sole uh, foot soles of the left and right legs. However, to use to define stability margin, to uh, we probably need to project things to 2D and come up with a unique, come up with a consistent measure. So there have been works in this area. First, we investigate how the ZMP moves as we apply force. So in this case, a rotating force is applied, and in this case, an oscillating kind of force is applied. You can see that when both the legs are on ground, which is the case of orange and the green graphs, uh, compared to the blue and red graphs, where one of the legs is on higher ground, uh, you see the red and blue graphs are shifted towards right. We'll talk about why their magnitudes have changed later, but we can clearly see that they have moved towards this foot, which is on higher ground. Now, this means that the stability margin in this case is less. Uh, but we know from but we know that it is difficult to tip the robot on the side of higher ground than on the lower ground. So this calls for modification of the support polygon. Now, method in literature says that we project the support polygon with focus at center of mass. However, this has an issue that uh, the ZMP does not always pass through the center of mass. If there is non-negligible moment about the center of mass, then the ZMP axis uh, separates out from the center of mass, and this projection method is no more consistent because in in a plane, so this is called virtual horizontal plane. So this plane, if we take it up higher somewhere, then it may happen that the ZMP lies outside the support polygon. So what we have suggested, that is the solution, is that we take a point on the ZMP axis and then project with it as focus. Now this work is supposed to be published in upcoming journal, and it's novel. Lastly, I will come towards uh, the work on hardware. So at the moment, the simulation that you are seeing is replication of motion in software, an open loop replication motion in software. Now, the motion is actually input in real time to a keyboard and is replicated at 60 hertz, and it is rendered as well. Ultimately, we want to perform full closed loop push recovery experiment with computation happening on the computer. So this is the communication network. We have a single RS-485 bus with multi-drop kind of framework, where the actuators and the sensors are connected to the bus through microcontrollers. Now, all the computations are supposed to happen on the computer, and based on the sensory input, we can command the actuators. Now, this whole loop is supposed to run at 100 hertz, and both way communication has been tested, but the speeds and the complete simulation has to be achieved yet. So this is a robust data packet, which is transmitted over the line to avoid any errors. We have used these FSRs, as you can see here on the foot. This load concentrator has also been designed. The FSR calibration circuit and setup has been made. We have some issues in calibration at lower end because of lightweight robot. So this robot weighs only about 1.5 kgs. So these sensors, when they are unloaded beyond the limit, they do not perform well. So there are a few challenges here, but in higher weight zone, they're working fine. Lastly, again, in the area of push recovery, inclusion of actuator dynamics or link compliance is novel. We can see in simulations of mostly in the single leg stance, in the simulation, you can see that legs are passive. However, in practice, you can see them hitting each other. Now, this can be this can be sorted with compliance compensation. We have measured the compliance at the hip and the ankle brackets, which we found to have significant some compliance. And we have also measured the gearbox compliance with high resolution encoder. And we have plotted we have found out the stiffness curve, load deflection curve. And we intend to model this as a series elastic compliance, which makes it easy instead of link compliance. So this is again a part of upcoming journal publication. So I would like to thank PMRF for funding purchase of this robot, Kondo. It is a full body robot. It is not yet used in work, but it is supposed to be useful in the standing up from fallen position problem. Thank you.